So 1D on 217 asks us to sketch a graph of the sketch a graph of the instantaneous rate of change of negative sine x as a function of x. So negative sine x is essentially just like the flipped version of sine x. So we can actually see a graph of this in our textbooks here. So I would maybe just sketch this over one cycle, so maybe from 0 to 2 pi. So using the slopes that we talked about yesterday, okay, we know that the slopes at minimums are 0, or at their middles are just slopes of 0, right, at the turning points. We also know that the minimum slope of just like a regular sine x function or the flipped version are negative ones and positive ones, minimums and maximums. So if we look at that graph on part 1 here, we can see at 0, the graph is actually decreasing, and that tells me that the slope of the tangent is negative 1. At pi over 2, we are at a turning point, so the slope of the tangent there is 0. And then at pi, we are increasing, and at that point of inflection, so our slope of the tangent is 1. And then we want 3 pi over 2. Slope of the tangent at that point is at a turning point. And then at 2 pi, slope of the tangent is decreasing again, so it's at that point of inflection, it's at the minimum slope. Okay, so when we go to sketch this, we're just going to sketch again over the one cycle here. And I'm just going to kind of like plot these out. So it actually should end up just being like a flipped version of cosine, I think. So that's your graph of the derivative of negative sine x. Okay, so that's 1D. For part 2, I think we can maybe extend this idea to negative 4 cos x, although because we're stretching it by 4, that actually does change the slope of the tangents. They're not like negative 1 and 1 anymore. So that one was maybe a little bit more challenging. The original graph of cosine, so if you guys remember last year, we talked about the key points of cos x, and the key points were 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and 2 pi, 1. This is like the regular graph of cosine. Yep. Pardon?
I have a question about 1.
Sure, 1.
Yeah, for C, like, remember how we're solving for like a little bit to the left and a little bit to the right?
Yep.
Is that what
I don't think that's necessary for part C because we've already figured out for a regular sine graph what the slopes of those tangents are. This one's just a flipped version of that. So the slopes of the tangents have just been like altered. Instead of like being positive 1 and negative 1, they're now negative 1 and positive 1. So because there's no stretch or anything like that, the slopes of the tangents are still 0, 1, negative 1. Okay. Okay, so when I have the function y equals negative 4 cos x, what is this transformation that's happening to this function here?
vertical stretch by a factor of 4 and vertical horizontal reflection over a horizontal axis.
Okay, so we have a stretch by a factor of 4 and also a vertical reflection. So basically I'm just taking all my y's and I'm multiplying them by negative 4. This is my new graph of negative 4 cos x. Okay, so vertical stretch by a factor of negative 4. So essentially it should look pretty much the same as the cosine graph, but instead of negative 1 and positive 1, we're going between negative 4 and positive 4. So like so. Oh yeah, true. Thank you. this way. Okay, so there's our graph. Look how beautiful. So this one, because I've now stretched my graph, my slopes of my tangents are, of course, at the turning points, the slopes of the tangents are still 0, but at those maxes and mins, where I have like the steepest tangents, the points of inflection, the tangent slopes have changed. So you're gonna have to, I'll let you kind of move forward with this, use kind of what we did in the lesson, to see if you can maybe find something. Maybe we want like a point on the very left side of pi over 2 and the very right, so that we can find the slope of the secant at that particular point, so that we can estimate the slope of the tangent. Yeah, so maybe we would choose something like, I'll give you maybe like a bit of some direction here. We could consider pi over 2 to maybe be something like 400 pi over, no.
Could you just do like pi over 1.99 and pi over 2.01?
Yep, you could definitely do that. Yep. We could also just think of this as like, we could also just think about this as, I don't know, you can do anything as long as it reduces back to 2. So if you decided to do like 200 over 400, as long as this reduces back to 2, I could do like 199 pi over 400 and then like 201 pi over 400 and find the slope of the secant over that. The name of the game is just trying to shrink the interval as much as possible. So if we go like a little bit bigger, we can maybe find something that's like a bit closer. But if you're not quite sure, you just want to make sure that like the 200 divided by 400, that reduces back to pi over 2. So that's kind of what we want to do. So you're going to find the slope of the secant over this interval. Yep.
And then when you're graphing, at the ends of the graphs, are you supposed to put arrows?
What do you mean?
So when you're graphing something that keeps going.
Yeah. So like this, you mean?
Yeah.
Yeah. Yeah. Devin?
So you want to make it as big as possible, is that what you're saying? Like, why do you make it 200 instead of 500? You just expand.
Yeah, we're just kind of like making it bigger so that we can find something that's like really close to pi over 2 on both sides. Yeah. There's a bunch of different ways that you can do it though, and I'm sure you can find, like, did you find a good estimate with yours?
I got 2, but I don't think that's right.
No?
I'm pretty sure it's 4.
Yeah, because it's stretched by 4. That would make sense.
So I should probably use a smaller interval.
Yeah, probably. Pardon? So the question is asking us to sketch a graph of the instantaneous rate of change, but I need to know what the slopes of the tangents are at those points of inflection, so at pi over 2 and at 3 pi over 2, in order for me to actually graph.
So if we didn't do that, our graph is
Pardon?
If we didn't do that, is our graph
Probably, yes. Question?
Wait, wouldn't the slope just be 4?
I think part of this is just like proving that, okay, if I stretch the graph by a factor of 4, does the tangent slope also stretch by a factor of 4? Or
On the test, we'd have to prove it.
I think that would be a good thing just to make sure. Do we need to do this calculation? Are we good? Okay. So that's kind of your starting point. You need to find the slopes of the tangents. Lewis? Yep. Pardon? You can just state the intervals that you see on the graph in the textbook. That's fine. You'll probably maybe start to see a pattern if you list the intervals and then. Shh, guys. Yeah, you could do something like that. That would be fine. Okay. Let's move forward here. Are you going to write your test? Okay, it's in the Learning Commons for you, okay? Okay, so I'm going to do a quick proof. So we've kind of like proved by investigation what the slope of the tangents are on sine, and then we kind of graphed, and by that we assumed that we made kind of a jump in our logic in saying that the derivative of sine was cosine. Now, we still used the slope of a secant to estimate the slopes of the tangents. So we haven't proven definitively that the derivative of sine is cosine. We have proven within a good range that the derivative of sine is cosine, but we haven't proven it for sure. So what we need in order to prove the derivative of sine is, of course, the Newton quotient. Okay, so we're going to use Newton quotient. You need to know everything. Okay, and what ends up happening with this part of our kind of like proof of this is that we get to a point where we actually have to do some observation of some graphs. So we are going to also use Desmos and observation of graphs to help us with this proof. We are also going to use some trig identities, which is why I printed you guys a trig identity sheet. Thank you very much. Okay, so we are going to go ahead and so in order to plug into our Newton quotient, we need sine. So obviously we need the function f at x that we are trying to find the derivative of. And we need f at x plus h. We always need that to plug into the Newton quotient. So f at x plus h in this case is the sine of x plus h. And then, so can I ask you guys, is the sine of x plus h equal to the sine of x plus the sine of h?
No.
What is it equal to? So what about the h part of that? Okay, so essentially we're using that sine addition formula under the compound angle. So if you look at your trig identity sheet here, we are using the sine addition formula to expand that out. You can pre-expand it out if you'd like. Sorry, I'm just trying to find my thing here. Huh? So think, if you look at your trig identity sheet, do you see sine of x plus y? So basically the y in there is like our h here. So this is going to expand out into the sine of x times the cos of h. Oh no, yes. And then sine of, or cos of x times the sine of h. Okay, this is what I'm going to use in my Newton quotient. Again, I'm using a trig identity to do this, the compound angle trig identity. And we're going to sub into our Newton quotient here. So we know we can find the derivative by taking the limit as h approaches 0 of f at x plus h minus f at x over h. So we're going to sub in what we have here, remembering that we rewrite that limit notation. So our sine of f at x plus h is what we expanded above. Okay, and I'm going to do a tiny little rearranging here. And I'm actually just going to move this in between these two terms here, just so that I can work with this a little bit differently. My thought behind doing this is that eventually I'm going to have to kind of like split these into their own pieces. And I have a common sine x in both of these two terms, whereas the last term that I'm putting on this new line here does not have a sine x in there, so I'm not going to be able to like common factor that piece out of there at all. Just rearranging. It's like 7 plus 4 plus 1 or 7 plus 1 plus 4, right? Same thing. Okay, so limits, when I do the limit as x approaches, or as h approaches 0, and I have multiple terms being added, I can actually take the limit of each of those individual terms. I don't have to take the limit of all of this together. So the limit of the whole thing is actually equal to the individual limits of each sum. Okay, so what we're going to do is we're actually going to consider this part right here. Sorry, I didn't mean to go through that. We're going to consider this part right here kind of like as a grouping. And then I want to consider this part right here as like a second grouping. And I'm going to split these guys into their own limits. So what we're going to have here is, oh, sorry, I totally just realized that I did not write that properly. Come on, people. You got to tell me these things. Limit as h approaches 0. Sorry. So we're going to split these guys into their own limits. Yep. So this is all over h, and this is going to be plus, because this is plus, the limit as x approaches, or h approaches 0 of cos x sine h all over h as well.
Do you have to write them again?
Yep, we're splitting them into their own limits, so we're actually looking at the individual limits of each of those pieces. Okay, and then over here, I can actually common factor a sine x, and limits, so again, actually, I'm just going to do that step first before I explain. We'll just do that quickly. Sorry. Actually, yeah, I'll just rewrite that part. Cos x. Okay, so when I do my limit, I'm actually only interested in the parts of the function that have h, because I'm looking for where the limit of those specific functions has h approaching 0. So the parts with x, which are sine x and cos x, are actually not going to be affected by the limit as x approaches h. Or, why do I keep saying that? The limit as h approaches 0. Agreed? If there's an x value in there, the limit is not affecting that. It just affects the parts of the function that have h's in them. So I can actually take these guys and I can just write them out front of that limit and focus on the parts of that function that have h's in them. Okay? So we are allowed to just kind of do this. Because it doesn't have any h in there.
What would that mean when
We're not going to put it on our calculator. We have to actually observe graphs of these things, because usually when we use Newton quotient, we like to like common factor and like cancel h's. But because we have h's on the bottom and our h's are kind of like in sine and cosine, there's no way that we're going to be able to cancel that. And that's kind of the problem that arises when we're trying to do these proofs. So I actually need to take a couple minutes and just observe the graph of cos h minus 1 over h and also sine h over h. Yep.
Just explain why you can put the x's in front of them.
So if I'm looking at the limit as h approaches 0, the parts with x's in that function won't be affected by the limit of h approaches 0, right? They're going to remain the same. Yeah, so I'm just taking out the part with the x because it's unaffected by h approaching 0. Okay, so I'm going to just scroll over to Desmos here. So this is the graph of the first one. And what I'm interested in, so this is, I replaced the h's with x's here just because Desmos we need y in x's in terms of y. So what we're interested here is the limit as we approach 0. So we're kind of like coming along here and we're looking at what we're approaching, what the y values are approaching as the x value is approaching 0 here. So what are we approaching as we approach 0? What y value? 0. Lovely. Question? Well, it's basically just because it's like a trig function within another function. So it actually kind of does this like weird thing where it starts approaching the asymptote, so it actually gets like closer and closer to the like an asymptote along the axis. But yeah, it's a little bit different because it's a trig function in there instead of like polynomials. Okay, so we are approaching, as we move both sides towards 0, we are approaching a y value of 0. So I think we can assume that the limit as we approach this graph right here is actually 0. So we'll have sine x times 0. And then here, cos x, I want to know what the limit of sine h over h is approaching as the h value is approaching 0. I'm using x's and desmos because it doesn't let me use h's. So looking at the graph of sine x over x, or in our case, we're looking for sine h over h, we are looking for what this graph is approaching. So what y value is being approached as the x values approach 0. So as we come from both sides here, we're looking for what we're approaching. Devin?
How do you know that it's 0? Like, if on a test I would have this, so how would I know that it equals 0?
Yeah, so you would have to, I would have to provide those graphs for you. Yep.
Like, so if you like plugged in values that were close to 0, wouldn't it give you like about 0 at the top, but then because of the bottom, like if you divide by 0.00001, it would start approaching infinity at that point?
So you're suggesting that we like input something like 0.001 into the equation
That's what like I was,
for both
that's what I
h's?
was thinking about it, yeah.
Yeah, we could probably do that. Just want to grab my calculator here. So let's suppose, I'm just going to use sine x over x. Let's suppose we did sine of like 0.00, I'll do 3 zeros. Yeah, it's actually not. One, two. Yeah, I think it works. So yeah, this is, the other option is we could choose a value that's like really close to 0, and we could evaluate it in that function for h. And I think that should also tell us. So Devin, that kind of answers your question. You can choose a value that's like really close to 0. So what is this guy approaching as we approach 0? 1. Okay, so the limit as h approaches 0 of this guy right here must be 1. And what do we end up with here when I multiply this whole thing by 0? Well, that part's gone, and cos times 1 is just cosine. So the derivative of sine must be cos x.
Can you just explain again why it's 1? Can I just see the graph?
Yep.
Are we going to have to derive that on a test?
So the graph, as we approach 0, you can see that the y value is approaching 1 here. Back to this.
Isn't that
Olivia.
function sine?
So that function is sine of x over x.
So when you put the 1 next to sine,
That, I think you're thinking of this part right here. This part we already looked at before. It was approaching 0. This part is what I just showed on the graph. So it's cos times the limit of that. Yep. Okay. Any other questions? Okay, so for the proof of the derivative of cos x, we're going to kind of make a bit of an assumption here. Our assumption here is going to be that we have already proven sine, the derivative of sine. So we're going to use that to help us with our proof of the derivative of cosine. And yeah, so we're going to use our transformation identities on our sheet. So if you look over at the transformation identities here, we can see that cos x is actually equal to two different things in terms of sine. It's equal to the sine of x plus pi over 2. It's also equal to the sine of pi over 2 minus x, and that's actually the one that we're going to use for this proof. There might be a couple different ways that you can actually prove this guy. Okay, and part of this is actually what I'm going to kind of use with you guys today. But what you do need to know in order to do this proof is that when we do the derivatives of sine and cosine, it's kind of like a chain rule thing where we do the derivative of the outside and then we have to multiply it by the derivative of the inside. So we know that the derivative of sine is cosine, now that we've proven it. So the derivative of this, so when we do dy over dx over here, the derivative of the sine part of this, we will get cosine of whatever is inside. Okay, in our little video that we watched at the beginning of the year, it was the derivative of the blob that's inside. So we get the cos of pi over 2 minus x. But then we have to multiply it. So this is the derivative of the outside. But then we have to multiply it by the derivative of the inside. So it's kind of like a chain rule thing. So what is the derivative of pi over 2 minus x? Keeping in mind that pi over 2 is just a number. Yeah, it's just negative 1. Good. And so we've got negative cos of pi over 2 minus x. Now, if you look at your trig identities one more time, you should see the cos of pi over 2 minus x somewhere on your transformation identities. What is the derivative, or sorry, what is cos of pi over 2 minus x equal to from your identity sheet? It's actually equal to sine x. So the derivative of cosine we've just proven is sine x. Or negative sine x, sorry. Okay, and again, the only reason that we were able to do this is because of our proof from above, because we were able to prove that the derivative of sine explicitly is equal to cosx. Okay, this is a trig identity right here. And this is also a trig identity. Zainab? Yep. Yep.
Where do you find the second identity on the table?
It's so on your sheet. It's under transformation identities. It's the third one down. Okay. So you guys have kind of like already had from this proof a little taste of how we do derivatives of trig functions. So for the rest of class today, we're just going to start by practicing some derivatives of trig functions. So the rule here, this looks kind of like complicated here. It's just the constant multiple rule. So it says that if I have some constant multiple times a function, it's equal to that constant multiple times the derivative of that function. So when I have something like 2x, the 2 will stay, and all I really have to do is the derivative of sine x. So when I go to do dy over dx here, my constant stays, and then I just do the derivative of the sine part. You could, if you wanted to, use product rule, but we know when we do the derivative of the first, we get 0. So it's really kind of like plus the first times the derivative of the second. That's the only part of product rule that matters. So the derivative of sine we know to be cos x. So that's our derivative. Okay, and then when we go to do the derivative of this, so the constant multiple stays, and we just do the derivative of the cos x part, we know that to be negative sine x. And then we just simplify here, negative and negative makes positive. Okay, it's basically kind of like a similar thing to like if I'm doing the derivative of 2x, I'm really doing I'm keeping 2 and I'm doing the derivative of the x part of that, which is why we just get back 2. Or if I'm doing the derivative of 2x cubed, I keep the 2 out front and I do the derivative of the x cubed part. So I end up multiplying the 3 by the 2. So same kind of idea of what we're doing here with the trig functions. Is everyone okay with these? Okay. Sum and difference rule, we've been doing this kind of all along with our polynomial functions. We just differentiate each piece. So when I go here, I'm going to do the derivative of sine, which we know to be cos x. And then I will do plus the derivative of cosine, which is negative sine x. And we end up with cos minus sine. Okay, and then kind of using our constant multiple rule and sum and difference rules, we'll take the derivative of each piece here. So this will be 2 times negative sine x minus 4 times the derivative of sine x, which is cos x, and that's our derivative. Any questions on these two? Ryan? So the derivative of sine x is cos x. So I'm just differentiating each piece of this. And then the derivative of cos x is negative sine x. Pardon? Oh, okay. Okay. So we're going to use derivatives to find our slope of the tangent where we have a point where x equals pi over 4, which means we need the special triangles. Guys?
Oh.
Guys? Anyone? Okay. Okay. So this is, the process hasn't changed here at all. What do I need to find slope of the tangent? Derivative. Okay, good. So the first thing that we need in order to find the slope of the tangent is the derivative, which is the general equation to find slope of the tangent at any point we want. And then we have a specific point that we need the slope of the tangent at, so then we will sub that in. So the first step in order to find slope of the tangent at a point is to find the derivative of that function. So we know the derivative of this function will just be 3 cos x. And then we are looking to evaluate the slope of the tangent at pi over 4. So we have our equation to find slope of the tangent. So we're going to plug in pi over 4. And just a reminder, your special triangles, you can add these to your trig identity sheet if you want like a place to have them where you won't forget them. Okay, this is our first special triangle. And if I'm looking for the cos of pi over 4, hopefully we know how to do this at this point, but we're looking for adjacent over hypotenuse. So the cos of pi over 4 is 1 over root 2, which is 3 over root 2 when we simplify here. Okay, or if we rationalize the denominator, we can also state this as 3 root 2 over 2. That's just with the denominator rationalized. Okay, so the slope of our tangent at that particular point is 3 over root 2, or 3 root 2 over 2. Which part? I'm just using the triangle over here, so I'm using adjacent and hypotenuse from the special triangle to evaluate cos of pi over 4. Any other questions for this? Okay, so you guys remember when I find the derivative, this is the general equation for the slope of the tangent anywhere on the function we want. Well, we want it at pi over 4, so we need to plug in pi over 4, right? So this is the general equation for slope of the tangent anywhere on our graph of f at x, right? Okay, so that's the definition of the derivative, right? It's slope of the tangent anywhere on the function. Good? Can we scroll? Okay. So same kind of idea. We're looking for first, so this one asks us for a tiny bit more. We're looking for the full equation of the tangent line. So first we need slope, and then we need a point on the line, and we need to find the b value. Okay, so first things first, we'll do what we did last time, which is first find the derivative. And then we want to know where the derivative, what slope of the derivative or what slope of the tangent is at pi over 6, I should say. So again, we're using our second special triangle. Lauren, Vanessa, can you grab the back door there for me? Okay, what is the cos of pi over 6? So this is the reference angle. So this is adjacent to the reference angle, and this will be hypotenuse. So it will be root 3 over 2. And the 2's cancel, so we're just left with negative root 3. Okay, that is our m. That's our slope in our equation for our tangent line. So this is what we have so far. And our goal is to find the b value in the equation of the tangent line. Okay? So I need a point that I know for sure is on the tangent line. What is that point? Where x is pi over 6. So I need the y-coordinate when x is pi over 6. So I'm going to just evaluate f at pi over 6 so that I can figure out what that y-coordinate is there. And then we'll plug it in to find b in the slope of the tangent. Oops. Okay, so our point on the tangent line is pi over 6, negative 1. Okay, guys, this process hasn't changed at all from our original process, like what we were doing in Unit 1. The only difference is that we're using derivatives of trig functions in there now, and we're using special triangles. Okay, so I'm going to sub in the x and y. And we're going to try to leave this in exact values as best we can here. Which means I just need a common denominator over on the left there. So I'm going to make negative 1, negative 6 over 6. And then my b value will be root 3 pi minus 6 all over 6. And that's what I'll sub into my equation. Olivia.
So only the 3 is under the root, right? For all of it?
Pardon?
Only the 3 is under the root?
Yes, only the 3 is under the root for both parts of this, right? For the first, the slope part, and also the b part. Any other questions for this one? We're all okay with this? Okay, so the general process if I'm trying to find the equation of the tangent line is I need derivative. I need to evaluate the derivative at whatever x value we're looking for the slope of the tangent at, and I need a point on the line. The only point that we ever know is on a tangent line that we have found is the point over which we're trying to find where the tangent line skims, right? So I only know for sure that the point where we're trying to find the slope of the tangent, this x value, that's the only point I know for sure is on my tangent line. We don't know any other point for sure on the tangent line. So I need to find the y-coordinate for that point using the original function, and then we plug into our slope y-intercept equation to solve for b. Yep.
So we'll always be given a point on the tangent for
If you have to find the equation of the tangent line, yes. Yep.
You don't have to like work backwards to that.
What do you mean by that?
Like you're not gonna give us like an equation like this and that we need to work backwards from it.
To find what?
Where the point is.
I don't think so. Okay. Good. So I have a worksheet. I'm going to stop that.